In this video, we are going to be talking about Dalton's law of partial pressures. So it was given by, surprise, John Dalton in 1801. So what this law is all about is going to be about, the pressures, okay, and it's going to be of a mixture of non-reactive gases. And the word non-reactive is quite essential because if you assume, okay, these gases are going to react with each other, then you'd have another entity being present. So that in turn will lead to, various differences in what we'd expect. So according to this law, the total pressure exerted by a mixture of non-reactive gases is equal to the sum of the partial pressures of individual gases. So basically, we are talking about the pressure. So let's assume in this container, we have a mixture of A, B and C. Okay, now the pressure which is exerted by gases A, B and C will be equal to the sum of the pressure of the individual gases. I get that the boxes seem like that of different sizes, but the basic idea is that the pressure which is exerted by the mixture of these three gases A, B and C will be equal to the pressure which is exerted by A plus the pressure exerted by B and plus pressure exerted by C. Okay, so here we are using a new word called as partial pressure. So partial pressure is just the pressure which is exerted by one of the gases in the mixture. Now here we will be Now when we talked about pressures, obviously there are other conditions like temperature and volume which will probably change. So what we are considering is we are assuming that they have the same volume and they are having the same temperature. So volume and temperature are considered constant and pressure is calculated. So we get the equation P total equals to P1 plus P2 plus P3 plus so on. Basically, P total is the total pressure exerted by a mixture of non-reactive gases. That equals to the pressure of P1 or the partial pressure of 1 plus the partial pressure of 2 plus the partial pressure of 3 and so on. Okay, that is the partial pressure of individual gases. But the issue is generally when we talk about, when we extract gases, they will have some amount of moisture in them. The reason being, you obtain them or they are obtained over water. So they will consist of some amount of moisture, and so there's something called as vapor pressure of water is subtracted from the total pressure, and this is referred to as the aqueous tension. So basically the pressure of the dry gas will be equal to the pressure of P total, pressure of the individual gases minus the aqueous tension, which is the vapor pressure of water vapor at that particular condition. In your textbook, you've been given a table which consists of aqueous tension, that is the pressure exerted by saturated water vapor at different temperatures. So for each temperature value you've been given, for example, at 273.15 Kelvin, that is 0 degrees Celsius, or the freezing point of water, the pressure which is exerted by water vapor, or rather the vapor pressure, is going to be 0.0060 bar. So, and at 301.15, 0.0372, you have these values in your textbook. So basically at that particular condition, based on the pressure, based on the temperature, you will be subtracting the value of aqueous tension from the P total, and that will give us the pressure of the dry gas. Now there is another important thing that comes up. So when we talk about partial pressures, we can also talk about it in terms of mole fraction. So let me just draw a line over here. Right. So in terms of mole fraction. Okay. So basically we know, or rather we're taking this particular gas, or rather we're taking that this particular mixture consists of 3 gases. Okay, 1, 2 and 3. And the condition of pressure or the partial pressure for 1 is going to be P1. For the second gas, it's going to be P2. And for the third gas, let me do one thing. I'll write it vertically or horizontally. P1, 2 is going to be P2 and 3 is going to be P3. So we are telling that we have this gas mixture which consists of 3 gases, P1, 1, 2 and 3, and the pressure of each of these is going to be P1. Partial pressures are P1, P2 and P3 for 1, 2, 3 respectively. So we are assuming that the temperature in these 3 cases, this is going to be at a constant temperature and volume. Okay. So, and the number of moles of each of these is going to be N1, N2 and N3. Okay. So we're having 3 gases, pressures P1, P2, P3. Number of moles is the N1, N2 and N3, and this is at a constant temperature and pressure, constant temperature and volume, because that's what this law is based on. So we know, based on the ideal gas equation, P1 will be equal to PV is nRT, right? So P1 will be N1RT by V. Okay. Next, P2 will be equal to N2RT by V, right? And P3 equals to N3RT by V. Right. So we have 3 pressures, partial pressures. Now we are taking the Dalton's law of partial pressures, where P total equals to P1 plus P2 plus P3 plus so on. So P total equals to P1, that is N1 RT by V. Now R is also going to stay constant because it's the universal gas constant, plus N2 RT by V plus N3 RT by V. Now these 3 values are constant, right? So we will remove it out. So we get N1 plus N2 plus N3 whole into RT by V. Okay, now what we're doing is we're going to be dividing the value of P1 with P total. So we are figuring out P1 divided by P total. Why we are doing this, I'll tell you in a minute. So P1 value is N1 RT by V and RT by V, right? So basically when you divide these two, what will happen is, I hope like you have the basic idea of math, and that's going to give us N1 by N1 plus N2 plus N3 into RTV by RTV. This and this gets cancelled. Because it's constant, we will be cancelling these 2 values. Now, mole fraction, if you remember, you've learned about mole fraction in the first chapter. And according to that, just give me a second, the mole fraction is equal to the total number of ratio of the total number of moles of one component to the total number of moles which are present. So there we had a solute. So for a substance which has a solute and a solvent, okay, so for XA, where A is the solute, mole fraction of A, that is XA, is equal to number of moles of A divided by number of moles of A plus number of moles of B. Mole fraction of B is going to be number of moles of B by number of moles of A plus number of moles of B. So here we have the number of moles of 1 divided by the number of moles of 1, 2 and 3. And 1, 2, 3 are basically the components in this particular mixture of gases. So the same thing can be applied here as well. So P1 by P total will be equal to the mole fraction of 1. So P1 equals to X1 into P total. So the mole fraction and the partial pressure are related like this. So the partial pressure equals to the mole fraction of that particular component into the total pressure of the mixture. Similarly, we get other relations as well. We get that P2, similar. It's the same thing that will happen. We'll get P2 will be X2 into P total. P3 will be X3 into P total. So from all of this, we can get a general equation that PO, the pressure, the partial pressure of the ith component will be equal to the mole fraction of that component into the total pressure of the mixture. So that's about it. So we talked about, just give me a second. So basically this is helping us calculate, we are getting this general equation where we are relating the partial pressure and the mole fraction, and this can be useful for figuring out or for the calculation of the pressure exerted by the individual gases or for the calculation of the partial pressures. So Dalton law of partial pressures was given by John Dalton in the 1801. According to this law, the total pressure exerted by a mixture of non-reactive gases is equal to the sum of the partial pressures of individual gases. The word partial pressure means that the pressure exerted by a particular gas. So here we have a mixture of 3 gases, non-reactive gases A, B and C. So the pressure exerted by A, B and C in total as a mixture is going to be equal to the pressure exerted by A plus the pressure exerted by B plus pressure exerted by C. And this obviously is going to be at a constant volume and temperature, because here we'll be measuring the pressure at this particular volume and temperature. You can't just change it, because obviously when there is a change in temperature, there's going to be a change in pressure as well. So that is why we are not, and obviously volume will affect pressure. So we are assuming that these volume and temperature are going to be constant. So P total, that is the pressure of the mixture, is going to be equal to the P1 partial pressure of the individual gases. So generally when we take, when we isolate a gas, we isolate it over water. So because of that, it will have a small amount of water vapor in it. So what we do is we subtract the pressure, the total pressure minus the vapor pressure, or in this, and that's basically the pressure exerted by the water vapor, and that's referred to as aqueous tension. Based on the temperature, you have the particular pressure that has to be subtracted, and that is given in your textbook. Next, we moved on to figuring out how mole fraction is related to partial pressure. So we took up an example which consists of a mixture of 3 gases, 1, 2 and 3, and the corresponding values of pressure are P1, P2 and P3 for 1, 2, 3 respectively. And obviously there is going to be, they have a different number of moles in each case. So for P1 it has N1 number of moles, P2 has N2 number of moles, and P3 has N3 number of moles. And all of this is going to be under constant temperature and pressure. So we can get the ideal gas equation as P1 equals to N1 RT by V. P2 is so and so, we're just substituting N2. RT and V are going to be constant because R is the universal gas constant, and we have taken the condition as volume and temperature staying constant in this case. So P total is going to be this particular equation, and we are removing out N1 N plus N2 plus N3 into RT by V. And we are dividing the P1 by P total. Now mole fraction is basically the mole fraction of a particular substance will be equal to the number of moles of that substance divided by the total number of moles present in the mixture. So here you have, I just put down the equations that you learnt in the first chapter. So for a mixture which consists of A and B, mole fraction of A equals to number of moles of A by Na, number of moles of A plus number of moles of B. Whereas XB, that is mole fractions of B, is going to be number of moles of B by number of moles of A plus number of moles of B. So P1 by P total is equal to N1 by N1 plus N2 plus N3. So this in turn means that this is the mole fraction of this divided by total number of moles which are present, that's N1 plus N2 plus N3, and that's how we got the mole fraction of 1. So P1 equals to X1 into P total, and P2 is going to be X2 P total, P3 is X3 P total. So from this we are getting a general equation, that is Pi equals to Xi into P total, where I is the ith substance or the ith gas. The partial pressure of the ith gas is equal to the mole fraction of that particular gas into the total pressure exerted by the mixture of non-reactive gases, and that's quite useful for the calculations which you'll be coming across. So that we're done with the Dalton's law of partial pressures. Honestly, for a second, when I first came across this particular derivation, I sort of, it was a little new, but not new, I would say, but I just had to write it down on my own and try and comprehend it. And I would suggest you to do the same. And the moment you try writing it down and, figuring it out, okay, this is equal to this, you'll automatically get this. Okay. With that, we're done with this Dalton's law of partial pressures. In the next video, we'll be, I think you have a numerical, so we'll be solving that and then continuing with the chapter.